and I'm claiming in one of his papers, he presents this hypothesis that I want to bring attention to. And the structure of my talk is going to be fairly straightforward, fairly linear. I'm going to go from, it's going to follow logically one thing to the next, right? So that shouldn't be too much of an issue. We'll see as we go along. So to start off with, two senses of relativity. Is everything okay?
Yes.
Yes.
Okay, speaking. Okay. All right. So to start off with, two senses of relativity. That's going to be the first section of the talk. All right. So here I'm going to talk about a distinction between two senses in which we use the term relativity in physics, two kinds of relativity principles. Relativity principles belonging to subsystems of the universe and relativity principles of the whole universe. And I'm going to emphasize that we should really make a distinction between these two. So in the first case, in subsystems, what I'm talking about here is a symmetry of space, which enables, which means that the relativity of space under transformations, which you can actually carry out, right? So this kind of symmetry has to do with the fact that I can do experiments over here, over there. I can go on a van and go on the motorway and do an experiment, and certain kinds of experiments will give me the same results no matter which one of these situations I'm in, right? And this is not something I could have known a priori. It's rather a generalization of an empirical result. And it's also never perfectly true of the real world. It's never actually perfectly applicable in the real world, because if I was to take into account like the gravitational effect of the walls of this room, for instance, I would realize that as soon as I move my laboratory from here to here, there actually is a slight difference. It's just that that difference is so small that I can, it's negligible. So the applicability of this kind of relativity principle is only true in virtue of an idealization. And some key examples of this are Galilean relativity in classical mechanics, and then the Poincare-Einstein relativity principle of special relativity theory.
Yeah, to call it an approximation rather than idealization.
Yes, well, it's approximately true of the real world, but the idea is that in physics we're going to model things as if it's perfectly true, and so we're replacing the real empirical situation with an idealized version in which we pretend like it's perfectly true, so that we can apply mathematical reasoning. Okay, and this kind of, in subsystems of the universe, we've known for a long time, right, that you don't get the same physics if you rotate it. So you tend to get similar physics if you move at a constant speed, or if you move your laboratory to different locations in space, or do experiments at different moments in time. But if you start rotating your laboratory, you have accelerations and no longer have the same.
But that's an idealization too, right? I mean, the Earth is rotating, so.
Yes, so it's rotating slowly enough that in those cases it's negligible.
Yeah.
In certain situations. But yeah, of course, there's more idealizations. But
why is it the same then?
Well, we're going to get to it.
Okay. Sorry.
Okay. So then the second type of relativity principle is, I'm going to argue here, is a totally different sense of relativity. And this is a sort of a priori necessary kind of relativity principle. This is relativity under Leibniz shifts. And the term Leibniz shifts comes from Leibniz clock correspondence, where Leibniz imagines a universe shifted or moving at a constant speed or at a variable speed, but where everything in the universe moves in the same way, right? And here, the point is that there is no difference in the relations of things if I take the whole universe and shift it by 5 meters, or if I boost it, or even if I spin it, right? There's no difference if I take the universe to include everything that's physically real. So, yes.
He's saying it's a priori, but in an Aristotelian universe it's false.
Yeah, it's a priori because it comes from the definitions of our words, right? So the Aristotelian universe would implicitly be using different kinds of definitions, right? And to be more specific, so it's analytic a priori. It's part of the definition of the term whole universe, right? So in the context of like modern relativistic physics, we'd have to include in the term physical things like the metric, space-time metric, other things that have causal influence on the real world. So yeah, so this is a different sense of relativity, and it follows from the definition of the universe, material things that exist in it. And in principle, this should be true under any shape-preserving transformations, where the shape is a relevant, physical, real relations between things that exist, right? So any shape-preserving transformations, such as rigid transformations, should restore the same physics, right? And note that physics is usually only really concerned with this first sense of relativity. And I think there's been some confusion historically, and you can look even in like people like Poincaré's writings, between these two senses of relativity because of this. That people thought the relativity principle, many people suggested the relativity principle is like a necessity of thought, it's true a priori, based on this kind of reasoning, but then immediately applied it to cases like this without taking into account the fact that in classical mechanics, for instance, it's actually a generalization of an empirical result. It's, because the relativity principle in a classical system is not true a priori, because it's only true in virtue of the fact that we can usually neglect the influence of the environment, whatever that environment might be composed of.
Could I clarify, is the second thing, I don't know if you're familiar with Nick Hagett's term kinematic relationism, is it supposed to be the same? Or? No worries.
I'm not familiar with that term, but it sounds like it could be. So Mach's principle. So unlike what I just said previously, where most of physics is only concerned with the first sense of relativity, Mach's principle has to do with this second sense of relativity principle, this a priori requirement, right? Now to explain what this really consists of, so I'll give you the context. So for Newton, the appearance of inertial forces in non-inertial frames was evidence of the reality of absolute space, which defines true motion, right? He has this famous bucket experiment, I'm sure you've all heard of, to prove the existence of absolute space. Oops. Okay, there we go. So yeah, indeed, in order to properly define the notion of force, like an influence that causes an acceleration, we need to know what motion bodies will resort to in the absence of forces. So we need some kind of law of what bodies will do when there's no forces present. We need a law of inertia. And so classical mechanics is based on this paradigmatic distinction between forced motion, which is motion subject to causes, and uncaused motion, inertial motion, right? Now, what I've argued in my paper on Mach is that for Mach, this distinction is illusory, and that's his essential thesis there, right? Is that there isn't a fundamental distinction between caused and uncaused motion. Indeed, all motion is just as caused as any other motion. It's just that inertial motion would be caused by, well, what's been termed inertial motion in classical mechanics is caused by some kind of homogeneous aspect of the environment. That's why you get this homogeneous motion, this constant speed, constant direction, okay, with respect to that environment. And the idea here was then that once the environment has been taken into account, we no longer have a distinction between forced and inert motion, and we don't need this concept of an absolute space reference frame, right? And this will allow us to then extend the relativity principle once the entire environment has been taken into account, so that we will have symmetry under arbitrary rigid transformations. So that was kind of like the vague program, although I think it was, articulated poorly in many places, even by Mach himself. But that was kind of like how the program was in the late 19th century.
Can I make a remark about, can you return
Yeah,
to the
yeah.
previous? So about the classical mechanics based on the distinction between caused and uncaused motion. But so if you have an inertial world line, a straight line, then according to Newton's law of motion, it says that the total force acting on the body is 0.
Right.
So there might be multiple causes, but they cancel each other out.
Yeah.
So they call it uncaused is not really what's going on.
I mean, you're right about that, but there's still underlying that the notion that if all of those causes were to be subtracted, there would still be a motion defined, which would be, so if you did take away all of the causes that you know about, it would result to inertial motion. Otherwise, the system doesn't work. So that's, yeah, but that's a good point to point out. Okay, so Mach's principle. So what I've called Mach's principle, which I'm going to distinguish between Mach's principle and Mach's hypotheses. That's one of the main things I've tried to do in my paper, my previous paper on Mach's principle. Is I think there's been so much confusion because everybody calls this thing Mach's principle when in fact it's a hypothesis most of the time that they're talking about. So yeah, so Mach's principle as this way of defining the whole universe as the totality of things you have a causal relation with, is agnostic about what the actual cause of inertial motion is. It simply requires that we find some kind of cause for inertial motion, that we don't accept this idea that motion can happen without a cause, right? And so in his work, actually, Mach proposes 2 hypotheses, which is not what most people don't even know about this. He proposes 2 hypotheses. So if we define Mach's principle as a requirement that inertia has a physical origin, and then we ask the question, what is that origin of inertia? He proposes 2 possible hypotheses. Mach hypothesis 1, that space is like a literal physical medium that is causally responsible for determining the inertial motion. And Mach hypothesis 2, that physical space, this is the one that he prefers, is really an abbreviated reference to something that we're more familiar with being material, which is the masses of the universe. And these are the sources of inertial influences. So yeah, so there's 2 possible hypotheses here. And of course, the one we're going to be most interested in is going to be Mach hypothesis 2 for the purposes of this talk. So yeah, so is general relativity Machian? I'm not going to spend much time on this. This is not the topic of the talk, but very briefly, I'll say that once we've split Mach's principle, made the distinction between 2 different hypotheses that Mach suggests, general relativity theories like this can kind of be seen as Machian in the sense of Mach hypothesis 1, in the sense of space becomes something physically real in general relativity, and is responsible for determining inertial motion. But it's a kind of hybrid between Mach hypothesis 1 and Mach hypothesis 2, because since there are also these inertial induction effects, such as the Lens-Thirring effect, the masses of the universe are partially responsible for inertial motion in local frames, right? But they're not entirely responsible, depending on your cosmological model, right? So it's a kind of hybrid theory. But yeah, next, Reissner's hypothesis. Now this thing I call the Reissner's hypothesis, everyone in the literature doesn't really know what this means. Well, they call it Mach's principle, and then they don't know what it actually implies because they think it's just a relativity principle. So again, I'm trying to clarify things by distinguishing these different ideas with different names. So although Einstein did not produce a theory which successfully implemented Mach hypothesis 2, the second hypothesis of Mach was nonetheless crucial to Einstein's reasoning on his way to general relativity. And he referred to this idea as Mach's principle, although I've argued this is a misnomer. His key contribution for our purposes was articulating the equivalence principle, which I claim should also really be called the equivalence hypothesis, which it has sometimes in literature. And this is a generalization of this observed result that all objects with accelerating in the gravitational fields form with the same acceleration. And you can express this as like the gravitational mass and the inertial mass is equal. I'm not going to get into the subtleties of the equivalence principle or equivalence hypotheses. I'll just take it in the broad sense to indicate that gravity, like inertial forces, is a universal force. It acts universally on all things. And this suggests a possible unification of gravity and inertia. So the equivalence principle for our purposes is going to be, this idea that suggests the possibility of unifying gravity and inertia. If the equivalence principle didn't hold, this wouldn't be possible. So taking Mach's hypothesis 2 that we looked at just before, inertial motion is conditioned by the masses of the cosmos, and combining it with Einstein's equivalence hypothesis that gravity and inertia are the same in their very essence. That's the quote from Lenkel's paper. He calls this like the Einstein equivalence principle. I think it just captures like the idea I'm trying to get across with the equivalence principle here best. The combination of these two sort of suggests this even bolder hypothesis, which I'll call like the Machian gravinertial unification or Reissner's hypothesis. And this is the idea. I mean, you can already see the two kind of make sense together, right? We know that the gravity is an interaction between masses. If gravity and inertia are the same in their very essence, this kind of goes well together with Mach's hypothesis that inertia is also due to an interaction between masses, right? And so the combination of these two suggests that by relativizing inertia, by making inertia be defined relative to masses rather than to absolute space, we're automatically going to get gravity out as a side effect because of the inhomogeneity in that distribution mass, right? Unlike absolute space, which is absolutely homogeneous. Okay, so that's the very vague hypothesis that's called Reissner's hypothesis. And yeah, so the idea here is the physical properties of space that constrain the motion of bodies are due to an interaction with other bodies, and this interaction is mediated through the force which we call gravity. Now, although Reissner's hypothesis is only really conceivable once we've taken on board the significance of the equivalence hypothesis, the first mention of an idea along these lines goes back all the way to 1896 in this little booklet by Benedict and Emanuel Friedlander. And Emanuel Friedlander is responsible for writing this section. So here's a quote. However, it seems to me that the correct form of the law of inertia will only have been found when the relative inertia as an effect of masses on each other and gravitation, which is also an effect of masses on each other, have been derived on the basis of a unified law. And he even goes on to suggest that this might be done through the application of Weber's law for electromagnetism to gravity. And we'll see that that's very similar to the procedure I'm going to go through a bit later on. Okay. Now, yeah, why have I called this Reissner's hypothesis? Well, between 1913 and 1915, Hans Reissner was closely following Einstein's pioneering work on gravity. And in the second of these two papers, which is titled On the Possibility of Deriving Gravity as a Direct Consequence of Relativity of Inertia, he articulates clearly what I'm calling Reissner's hypothesis. Okay, this is the quote. Well, there's two quotes. So to begin with, he's looking at Einstein's equivalence hypothesis. He actually calls it the equivalence hypothesis in the paper, in German, of course. I was very happy about that. So yeah, Mr. Einstein's equivalence hypothesis, which asserts the mechanical and optical identity of an acceleration field with a field of constant gravity seems to imply a deeper meaning that gravity is also a resistance to acceleration. And then a bit later on in his paper, he writes, if I'm successful, gravity would be understood as a direct and necessary consequence of the relativity of acceleration. The identity of the gravitational and inertial masses would be shown to be self-evident, and the gravitational field would not only be equivalent to an accelerated space, as Einstein proposes, but gravity itself would be identified as a resistance to relative acceleration. So he's suggesting this kind of unification that goes beyond the procedure Einstein ends up carrying out in his theory, right?
Does optical mean empirical, or does it have a special meaning?
I think he's talking about the effect of gravity on light being equivalent to a field
of light. Okay.
Yeah, exactly. So who was Hans Reissner? Very briefly. So yeah, this is him with his wife, Josephine Reissner. So interestingly, he was a pioneering German aeronautical engineer, and he was the first person to build an all-metal aircraft. So if you've ever been on a plane, all metal here means like that the body and the wings are both made of metal. So you can thank Hans Reissner next time you fly on a plane. He was also the first to derive the Reissner-Nordstrom metric in 1916, which is partially named after him. And for our purposes here, he's also the first to have, and pretty much the only person historically to have articulated this idea that I'm calling Reissner's hypothesis about explaining gravity as a phenomenon of relative inertia. So over the course of the 20th century, various papers were published that to varying degrees embody this idea of Reissner's. Although in all of these, the idea isn't particularly well articulated. It gets articulated in Reissner's paper. After that, it becomes much more popular for some reason for physicists to explain inertia in terms of gravity. So they kind of do it the other way around. For instance, Dennis Sharma's paper is called On the Origin of Inertia, rather than On the Origin of Gravity. I prefer doing it the other way around because to me, gravity is the unexplained thing. It could have not existed, whereas we need some kind of law of inertia necessarily, otherwise, where would things go, right? I spoke about it before. So these are some of the key papers. There's quite a few others, but yeah, I'm not going to look at any of these in particular. The model we're going to look at is mostly inspired from Dennis Sharma's paper from 1953, although I've done some significant changes to it. Hopefully you'll think in the right direction or make sense. Well, I try to do a relativistic extension. Anyway, unfortunately, apart from Reissner's papers, yeah, as I said, this is not expressed generally as an explanation for the existence of gravity, which I think is a shame because I think that's the boldest idea philosophically that's played here. So we're potentially explaining why gravity exists. So, okay, now onto the modeling gravitation. So I'm going to carry out this electromagnetic analogy of inertial and gravitational forces. First, we're just going to do an electromagnetic analogy with inertial forces, and we'll see how gravity comes out of that. Yeah, so let's get to it. So we begin by implementing Mach's principle. If you remember what I called Mach's principle, is this idea. So this is a quote from Mach. Obviously, it does not matter whether we think the Earth is turning around its axis or at rest, while the celestial bodies revolve around it. The law of inertia must be so conceived that exactly the same thing results on the second supposition as on the first, right? There's no absolute motion, and therefore we have to conceive the law of inertia in such a way that there is no difference between the two. So in order to implement this, we need to introduce these two force fields which appear. So I'm just going to consider for now, in classical mechanics, these inertial forces in a simple uniformly rotating frame, right? You need the centrifugal force, centrifugal field, and the Coriolis field, and these interact with your mass and momentum to produce these forces. And then written in terms of potentials, because you can write these fields in terms of potentials, they look like this. And we can kind of do like a relativistic extension of this and imagine this as a 4-vector. They will look like this. For now, I'll explain a bit more afterwards. And from a Newtonian perspective, this A mu would be interpreted as a property of absolute space. So maybe like from like a Minkowski perspective, where you have like the absolute space-time structure that's responsible for the inertial forces. So A mu would just be a field belonging to that space-time structure. But now we want to apply Mach hypothesis 2, as I named it before. So we seek the material origin of the masses of the universe. We seek the material origin of inertial frames in the masses of the universe. And this can be achieved simply by continuing the analogy we have with electromagnetism. If you notice, the equations I have here are essentially formally analogous to the equations governing electromagnetism. And so if we just continue the analogy, we can write A mu as this integral. This is like a retarded potential over the full momentum of the universe, right? Where this is just like the retarded time and distance along the light cone. And this gives us also, in another form, the field equation, like that, right? With this being the full momentum. It's the full momentum density, rather, throughout the universe. So now the problem is we don't know the strength of the coupling, right? So we've carried out this analogy with electromagnetism, but if the coupling isn't the right strength, we're not going to get the correct inertial forces. So we can determine the strength of the coupling by requiring that A mu produce exactly the right relativistic, centrifugal, and Coriolis forces. Okay. And to do this, we begin by considering a homogeneous universe of density rho in a frame in which this universe is rotating with an angular velocity omega. In cylindrical coordinates, the fundamental distribution will be given by this. And then we integrate this to get a 4-vector potential A mu. And then for simplicity, I've put a K here, capital K, replacing this term and the coupling constant. So we're going to have to remember this equation afterwards, just because we'll calculate what capital K has to be in order to calculate the coupling strength. Okay. Now, by decomposing the 4-vector potential into the scalar and vector parts, we can calculate the centrifugal and Coriolis fields, E and B respectively. This is what it looks like. Essentially, I mean, the terms you get here, it's considering a very simple case, so it's not as complex as it would have been. This comes from taking the derivative of the gamma factor. The gamma factors come from it, this being like full momentum. Yeah. And this looks quite complicated, but it turns out that once we calculate the forces, things actually kind of tidy up quite a bit. Now we consider a test particle which is co-moving with a rotating universe, right? So I've got a rotating universe, I've calculated the field this produces, and I consider a test particle which is moving along with it, and so which should be stationary with respect to the rotating universe. So this means that we want it to go around in a circle. Okay. So we want an acceleration to come out of this. That's going to, a centripetal acceleration. It's going to keep it going around in a circle. So yeah, so we do the analog of the Lorentz force law. So I've taken my E and B fields from the previous slide. I plug them in there, and it kind of looks like it's a mess, but then in the end, what was it again? Like these gamma terms turn into their own, like they package together into their own gamma. Anyway, it turns out really neat in the end, and you get exactly this, which is in fact the correct proper, which produces a proper acceleration like this, right? And this is in fact exactly the expected proper acceleration, provided that capital K is 1, right? And so now we've determined our coupling strength. And this tells us that the small k, the coupling constant we introduced before, must be given by this, based on the equation we had of the relation between small k and big K. And now finally, we can plug this back into our field equation and write it as so. Okay. And here I'm just writing phi minus 1, because this is essentially the scalar potential of the sum of the total mass of the universe over its respective distances. So this is the expression this is like the field equation we get. And notice that this is not a normal field equation, since the coupling introduces a dependence on the broader cosmic structure. So we don't have purely like local physics. There's a dependence on the distribution of the mass in the entire universe here. Okay. And now from here, we can examine what happens. So we've made sure that our law of relativized inertia produces the correct centrifugal and Coriolis forces in the case of a homogeneous universe. So now we're going to look at what happens if the universe is inhomogeneous. In particular, we're going to consider an idealized cosmos which is homogeneous and of density rho, apart from a single mass at the center of, given by this mass m, represented by this mass m rather. In this case, we see that the scalar and vector potentials will be given by these. Now I'm ignoring the relativistic factor because we're only going to be dealing with non-relativistic velocities in this case. So here, phi mu is the gravitational potential of the rest of the universe, so apart from the mass m, right? And this is the gravitational potential of the mass m, the scalar potential, sorry. It's not gravitational yet, it's inertial. Don't forget that. Okay. And now, since the universe in this scenario is not rotating, the vorticity is 0, so we don't even need to consider the B field. Instead, we just calculate the E field, and we take, an analogy with electromagnetism, this expression, and we get this result here. And now there's actually two approaches. So now we've calculated E. There's two approaches to deriving the acceleration of a test particle in this scenario. Either we can consider the acceleration induced by this field E in the frame in which the universe is stationary, so that A, which is the velocity of the universe, is 0 at all times. Or we consider how the universe moves, so how A changes with respect to an inertial frame, i.e. one which feels no forces whatsoever, right? So this is a frame defined by the analog of the Faraday tensor being 0, so that B and E fields are 0. This is a frame that only exists locally. Right? This is a free-falling frame. So we can also do this, and this is actually the procedure that Sharma carries out in his paper in 1953. And you don't even need to calculate the coupling strength of the field equation in order to carry out this procedure, because you get a balancing between the inertial resistance to your acceleration and the acceleration induced by the local mass. So you don't even need the coupling because it cancels out. But in our case, since we've already calculated the coupling strength, we can do either procedure, and in either case we get the same result. We get an acceleration of c squared over phi times m over r squared. And so this gives us a roughly m over r squared relation, right? Which, if you're familiar with classical mechanics, is essentially what you have in Newtonian gravity, right? So this is essentially just Newton's law of gravity, provided that this expression holds. The gravitational constant is equal to c squared over phi, or g times phi is c squared, right? So this is a very simple derivation of this result, okay, with this basic analogy with electromagnets. So thus, if this equation holds, what I'm claiming here, if g times phi equals c squared, where phi, again, is like the total sum of the masses divided by the distance of integrating over the entire observable universe. If this equation holds, we will have explained gravity entirely as a phenomenon of relative inertia. And this is what I'm claiming embodies Reissner's hypothesis. The gravity can be explained as a phenomenon of relative inertia. So what are the, how could we possibly test this kind of idea? Are there any implications this would have for cosmology that would allow us to potentially test this idea? So I'm going to look at what some physicists have suggested over the course of the 20th century. And again, like most of the ways people were thinking of this were quite vague. So there's a lot of lack of clarity in this whole literature. But anyway. So yeah, so this proposed gravitational unification has some analogy to Maxwell's unification of electricity, magnetism, and optics. In that case, you also got a similar kind of relation between these natural constants. C squared equals 1 over mu naught epsilon naught. That's in Maxwell's case. And this is the relation I'm proposing today. In the case of Maxwell, these values were already known, in the 1860s to a reasonably good accuracy. And so it was immediately obvious that Maxwell's theory predicts that light is an electromagnetic wave, right? Or it suggests this at least, right? But for us, this quantity phi remains challenging to count. There's no way to simply, especially in 1915, when these kinds of ideas were initially coming, when people were considering ideas like this at first, or 1925 more like, this was definitely not something that could be calculated. And even today, it's not really clear how we calculate the total gravitational potential of the universe. Okay. Maybe you guys will know more about that. Yeah. So nonetheless, we can investigate whether this equation might imply any further theoretical results that may be tested indirectly. So I'm going to look at 3 possible candidates. First, a relationship with Jordan's zero energy condition. Then the famous Dirac large number coincidences and the kind of Dirac-Eddington program of explaining natural constants. And then the critical density cosmos relation. And this is mostly based on ongoing correspondences with Alex Bloom, who's pointed me to some of these papers and so on. Yeah, so it's not hard to notice that this condition, G phi equals c squared, immediately tells us that the total negative gravitational potential of a particle that a particle has with respect to the rest of the universe is fully compensated by its rest mass energy, right? If this equation holds, I can just put m on either side, and this tells me that mg phi, which is my gravitational potential, equals mc squared. If the gravitational potential is negative, then each particle contributes 0 total energy, right? Now, in fact, this equation was derived for this reason totally independently of any considerations of Mach's principle in 1939 by Pascal Jordan. And this is a quote from his paper. We interpret this equation as the expression of the energy principle. It means that the added potential energies mc squared of all material particles are precisely compensated by the negative gravitational energy, so that the whole universe energy stays constant, namely virtually the whole. So maybe I should add also that both for Pascal Jourdan and for Dennis Schamm, who derives this equation in 1953 based on Mach's principle, this is a favorable result because they're working in this kind of steady state type concept where you have matter being created out of nothing. And so the way they're thinking is that if the total contribution of the matter that's being created is zero, then this means that you can have conservation of energy across matter creation, which is a favorable result for that. However, you know, I think even in a Big Bang type cosmology, this isn't necessarily irrelevant, right? To have zero total energy. Right. So this zero energy universe should. So yeah. So exactly why this result of having zero total energy in the universe should be associated with the Machian type universe is quite mysterious to me. I've been talking with Alex Bloom about this. You can ask me about it in the Q&A if you like. So yeah, so Jourdan's 1939 paper was in large part motivated by a paper from the previous year by Dirac, in which he points out these numerical coincidences having to do with these relations between the atomic scale and the scale of the cosmos. Yeah, I'm not going to go into what those are in particular. The point is, Jourdan then develops this theory further, and this is then taken up by Robert Dicke and Karl Brands, who combine this with their understanding of Mach's principle and even cite Sharma's results to develop the Brands-Dicke theory in the 60s. And I think other physicists have done this as well, but Wheeler and Dicke at various points, you know, in the context of GR, talk about using the lens-stirring effect to derive a similar approximate condition on a gravitational constant. But in that case, it's always an approximate condition. They don't give an exact equation. But this appears throughout the 20th century in dozens of papers, this kind of expression of G times the mass of the universe divided by the radius of the universe over c squared is approximately of order unity. Now, okay, now possible relationship to the critical density condition in cosmology. Now this, I can't point any decisive evidence for, but there is this recent book by C.S. Unnikrishnan, an Indian physicist, where he makes this claim. Yeah, I'm going to skip some of this quote. He just explains what a critical density is, and then he explains this can be interpreted as a natural constraint of energy conservation in the creation of matter in the universe from vacuum. Then the total energy before and after creation has to be zero. This is achieved when the universe has critical density at any epoch. Also, it fixes the magnitude of the gravitational potential as phi. This is the same as my g phi, right? It's phi underscore u. Meaning then the rest mass is matched exactly by the negative gravitational potential, making the total zero. So he makes this claim that the critical density condition is equivalent to this expression. I've never seen that proven, so I've sent him an email asking why he's claiming that, but I got one response so far, but it's not really clear what he's talking about. I think he kind of went discussing something else. So that's a claim I've seen around. Okay? It's not like a decisive result. So yeah, so I've not seen a rigorous proof of this, but yeah, actually I wrote this before. So in conclusion, I'm just going to go over a recap of what I've talked about today. What's the time?
Sure.
Okay. Am I like finishing early?
No, you have like.
Or just, okay, cool. All right, perfect. Yeah, so recap. So whereas for subsystems of the universe, symmetries and the relativity principle arise as idealizations, or idealizations of convenience empirical regularities, for the universe as a whole, it is analytic, depending on how we define the universe. This leads us to Mach's principle, that inertial motion is not motion in the absence of causes, but motion whose cause lies in some regularity. And as candidates for the cause of inertial motion, Mach suggested, Mach hypothesis 2, that the distant stars could somehow condition the inertial frame. In combination with the equivalence hypothesis of Einstein, this suggests Reissner's hypothesis that gravity is somehow the dynamical residue of this relativized inertial law defined with respect to the mass of the universe. And the idea can be realized in a theory which treats graviinertia, as I've called it, gravity and inertia, by analogy with electromagnetism. And it leads to this expression, G phi equals c squared. And the result suggests these curious cosmological implications, including a zero total energy universe and a possible prediction of a critical density condition. Okay, so I'll leave it at that. Thank you very much for this.